Hi guys, let's take a few minutes and look at the first 6 questions on our online review topics. So the first question just involves simplifying expressions, and this very first one is just combining like terms. I'm adding these expressions together. So 3x squared plus 5x squared, that makes a total of 8x squared. So 8x minus 2x is 6x. And then the negative 5 minus 7 gives me the minus 12 at the end. We're done. So this is just distributing. Something to remember when you take the 3x times the 5x, the 3 times 5 makes 15, but the x times the x makes x squared. So that x has an exponent of 1, and so does this x. So when you multiply them together, you add their exponents. Minus the 3x times the 9, well, the 3 times 9 is 27. There's the 27x. So all you're doing is simplifying expressions. So you're just combining the terms that you can combine. And notice here, there aren't any terms to combine. This is 16x cubed plus 12x squared plus 4x. None of these are like terms. This is an x cubed term. This is an x squared term. And this is a linear term. It just has x to the power 1. So there's really nothing to do here. You're stuck. 16x cubed plus 12x squared plus 4x. There's nothing to combine, there's nothing to multiply, there's nothing to simplify, you're all done. So in number 2, you're trying to find which expressions are equivalent to this, and this question is really just understanding what you can do with an exponent that is negative. So essentially this 5 to the negative second power, if you move it into the denominator, you can make it 5 to the positive second power. Same thing, this 5 to the negative 7th power, if you move it to the numerator, you can make it 5 to the positive 7th power. And now the exponents are positives, and we can continue simplifying. But the job really isn't to simplify. Our job is to determine which of the expressions are the same as this one. So this 5 to the 7th over 5 to the 2nd, that's actually answer C. So that is an equivalent expression. So notice this one is not. We're not going to get a 5 to the 9th. And same thing, the 5 to the 7th over the 5 to the 2nd, those won't cancel and make 1. But this is equivalent. So notice we have 5 to the 7th power in the numerator, 5 to the 2nd power in the denominator. So what that really is 7 5s multiplied together in the numerator, and in the denominator we really have 2 5s multiplied together. So you can cancel 2 of the pairs and you're left with 5 5s multiplied together. You're left with 5 to the power 5. So that would also be answer D. What I want you to see though is you don't have to work that hard by writing it all out. You can just subtract the exponents. 7 minus 2 will give me our exponent of 5. So question number 3, let's simplify this expression by using those ideas. So I can cancel the 30 and the 8. I can reduce both of those by a factor of 2. So 30 divided by 2 is 15. 8 divided by 2 is 4. So notice, I'll leave the 15 in the numerator, the 4 in the denominator. Now notice I have x to the 6th in the numerator, and in the denominator I have x to the 4th. 6 minus 4 gives me 2, so I can leave x squared in the numerator. And then I can move these terms with negative exponents in order to make positive exponents. The y to the negative 3rd will make y cubed in the denominator. The y to the negative 2nd will make y squared in the numerator. So notice if I take the 3 minus the 2, I get an exponent of 1, but there are more y's in the denominator, so that 1y will be left in the denominator. So my simplified expression will be 15x squared. Those are the components left in the numerator. And the y squared over the y cubed will leave me a y to the first power in the denominator. 4y to the first power in the denominator. And you don't have to write the exponent of 1. It's not wrong to write y to the first power, but it's not necessary. So probably the goofiest question is question number 4, because you're being asked to simplify. And to simplify this, I'm going to do something a little unconventional. I want to get rid of the decimals by multiplying the numerator and denominator by 100. But what I want you to see is 100 is just 10 to the second power. Well, look, I've got 10 to the 7th power in the numerator and 10 to the 10th power in the denominator. So what I'm going to do, multiplying by 100, I'm just going to borrow. I'm going to use some of these 10s right here. I need 2 of them to make a 100. 1.35 times 100 will give me 135. But if I've used 2 of these 10s, I have 10 to the 5th left. I'm going to do the same thing in the denominator. I'm going to make it a 725, but by using 2 of those 10s, I only have 10 to the 8th left in the denominator. So now I can cancel the 135 and the 725. I can divide both of those. I can see they both end in 5, so I can divide by 5. 135 divided by 5 will give me 27. 725 divided by 5, that's going to give me 145. But at this point, there's no more reducing that I can do. My factors here are 139 and 27, and 145 can't be divided by any of those. So I'm left with the 27 and the 145, and then all I need to do is work with my 10s. I have 10 to the 5th and 10 to the 8th. Well, if I take the 8 minus 5, that leaves me with 10 cubed. So I've got 10 times 10 times 10 still in the denominator. So in the numerator, I'm just going to have the 27, and in the denominator, I'm going to have the 145 times the 10 cubed. But 10 cubed is just 1,000, so I could write this as 27 over 145,000. So that's kind of a goofier question. The idea is just to recognize that you're working with powers of 10, and you can use some of your exponent properties to try and make things a little simpler. So simplifying radicals. So under the radical, let's break everything down under the radical, because essentially a radical means I can look for things that are pairs under the radical, and those pairs will help me do my simplifying. So let me start with that 40, and I'm going to make a factor tree with the 40. I suppose you can think of 40 in lots of ways. I'll think of it as 4 times 10. Well, 4 is just 2 times 2, and the 10 is 2 times 5. So there are my prime factors, 2 times 2 times 2 times 5. And then y to the 7th is really 7 y's multiplied together. So just for the sake of argument, for the sake of this problem, I'm going to multiply all of those y's out, because ultimately, to simplify the radical, you're just looking for pairs. So this pair of 2's gives me a 4, and I know that the square root of 4 is just a plain 2 outside of the radical. The square root of 4 is 2. So every time I have a pair, I can bring one of those factors outside of the radical. So I can bring a 2 outside of the radical, and I have 1, 2, 3 pairs of y's. So that means I can bring 3 y's, y times y times y, or y cubed, outside of the radical. And what that remains under the radical then, the 2 times 5 makes 10, and I have another y left under the radical. And we're all done. There's my simplified radical expression. So the last one I wanted to do on this side was number 6. And on number 6, the two things that we have 2 to the power 3/4, and then we have 2 to the power 3/14. And really what I want to do is just work with the exponents. You're just being asked to write 2 expressions that are equivalent to this. Well, the first thing that you could do, we have the same base of 2, so I can combine these just by adding the exponents. So I could think of this as one exponent of 3/4 plus 3 over 14. There's one equivalent expression. And I can simplify my exponent by making a common denominator. I can see my best common denominator is probably going to be a 28. I can multiply this fraction by 2 over 2. I can multiply this fraction by 7 over 7. And so I can make another equivalent expression. I can think of this as 2 to the power, this would be 21 over 28. Plus, this would be 6 over 28. That's another equivalent expression to the original one. Well, now that my denominators are common, I can write that as 2 to the power 21 plus 6, or 27 over 28. So this is an expression equivalent to the first expression. This is an expression equivalent to the first expression. That's why I keep using an equals sign. The other thing that you could do is write this as a radical. So the denominator of 28 is the index. So I could create my radical, and I can put the 28 here. And then the 27 is the power that I will put on the 2 under the radical. That's another equivalent expression that we could create. So you just had to create 2 equivalent expressions. Something that I wanted you to think about, this index of 28 right here, understand in a radical like you are used to in a plain square root, that index is 2. So that's why we were looking for pairs, 2 2s, pairs of y's under the radical. So it just so happens, though, that square roots are so common that we don't bother to write the index there. If we're working with a square root, you don't have to write the index of 2, but you can include it if you want to.